This lesson 5.3 has a lot of, like a lot of your lessons, has some pre-calculus implications. You will definitely see this again, maybe just a little bit more in depth. So what do we mean by inverse relations and functions? Well, to start with, you're not going to actually do problems like this, but I think it's a good way to maybe just lay some groundwork on what do we mean by the inverse of a relation. A relation is just a set of ordered pairs. So I have two different relations pictured here. If you're given a set of ordered pairs and you're asked to find the inverse, and this is pretty helpful when it comes to graphing, and you'll see that in just a little bit. It's pretty simple to come up with the inverse of a relation given a set of ordered pairs. We literally switch the coordinates within each pair. So if I wanted to know what the inverse would be, I would just take each ordered pair and I would switch the xy coordinates. So let me give you some a symbol that we use to represent the inverse of a function. And I know this says it's a relation, but we could also go one more step and we would say the blue also represents a function because there are no repeat domain members. So if this were the function called f of x, what I have here would be called the inverse of, and this is how it's written. That little -1 looks like an exponent, but it reads as the inverse of f. Okay, so letter B, again, I don't think we need to do this, but you get the idea. If you're given a set of ordered pairs, if this represented points on the graph of a function, and you were told to graph the inverse, you would literally just switch the xy coordinates within each ordered pair, plot those, and you would have the graph of the inverse. It's really that simple. So what if we're not given a set of ordered pairs, we're given the actual function? How do we come up with the inverse of this function? Well, in a way, it's like what we just did. Remember, if I'm giving you a set of ordered pairs, you just switch the xy coordinates. Well, if I want to find the inverse function, meaning the inverse in function form or equation form, I'm literally going to switch the xy variables. Okay? That's going to be my first step. It's really a two-step process. You switch places with x and y. Now you're probably saying, well, I don't see a y. Well, isn't it the same as saying y equals -3x? That means the same thing as f of x. So if you have to, I don't think you will, but if you have to, you can make this read as y equals -3x, and you haven't changed anything. Those are really synonymous. So if you want to find the inverse of a function, then literally trade places with x and y. That's your first move. So it's, again, related to what we just did with ordered pairs. And now solve for y. Two-step process. Switch places with x and y, and then solve for y. Okay, so to solve for y, I just multiplied by -1/3. You could have also divided by -3. And then the directions tell us to find the inverse. Okay, and what I'm going to do here, instead of saying y equals, since this does represent the inverse, and maybe it'd be a good idea for you to do the same thing, let's use that symbol to represent the inverse of. So if I'm given f of x, then this represents the inverse of f of x. All right, now the directions say graph the function. Okay, so let's start with, we'll call this the original. This is the one that we were given. Y equals -3x, so that has a y-intercept of 0 and a slope of -3. And just do your best to draw a straight line through those points. Okay, so this is the graph of the function f of x. Just label it like this. And then maybe in blue we'll do the inverse. Well, again, you have a choice here. It's pretty simple. This is just a linear equation. We could go through the same thing we just did. We have a y-intercept of 0. And we could count the slope as negative 1/3, up 1, left 3, or down 1, right 3. And we'll connect those dots. And so the blue represents the graph of the inverse. But you could have also, you wouldn't have been wrong, remember what we talked about in the very beginning of this lesson. If you know a point on the graph of the original function, let's just take, for example, negative 1, 3 is on the red. Well, for the inverse, it must contain negative 3, or 3, negative 1. If you just take those ordered pairs and switch places with them, then that's an easy way to come up with the graph of the inverse. And in some cases, when the graphs are a little bit elaborate, they're not just linear equations, this is a really easy way to come up with the graph of the inverse function. Here's something else I want you to take away from this. When it comes to functions and their inverses, and this is going to come back again as you get into deeper studies of math. A true function and its inverse will always reflect over this line. And what is that line? What's that equation? Y equals x, one of your parents. And what do I mean by reflects? Well, if you take the ordered pairs from the function and the inverse, they should be the same distance from that line y equals x. If we take the red, pick it up, and flip it over, it should pick up and flip over this line called y equals x. And that's always true. So you can kind of check yourself and make sure you've done the right thing. If you've got the original function and then the graph of the inverse does not reflect, the two lines together do not reflect over y equals x, you know something has to be incorrect.
So they need to be on the same line. Do they have the same vertex, like whenever they cross?
Not necessarily. Now they will cross y equals x, but not, let me give you a sample and you'll see this in just a minute. I could have a parabola. This is a rough sketch. If I have a parabola, if that represented the original, then that means the inverse should do something like this. It's like you pick up the original, literally pick it up off the page, flip it over, and you set it down on the other side of y equals x. And you'll see that more in some examples that I'll be doing in just a minute. Good question. Okay, let's try another one. Here is a function. It's called h of x. Well, let's find the inverse function. So right away, I'm going to treat this as though it's y, and I'm going to switch places with x and y. So I'm going to make this read as x equals y plus 4 over 3. So it's a two-step process to find the inverse function. You switch the variables, x and y, and then step 2, you solve for y. So in solving for y, the first thing I'm going to have to do is multiply by 3. And then obviously my next move would be to subtract 4. And since this does represent the inverse, I'm going to use this little inverse notation. This was h of x. This means this represents the inverse of h of x. Okay, and our directions are the same. We're going to graph what I call the original. If it helps, you could just rewrite this as 1/3 x plus 4/3 to put it in slope-intercept form. So that's a y-intercept of 1 1/3 and a slope of positive 1/3, so up 1, right 3. Or if you wanted to, you could go down 1, left 3. And we'll let the red line represent the original function, h of x. And then you have a choice. If you can identify literal ordered pairs off of the red, you could just take those ordered pairs and switch the xy coordinates, plot those, and you will have the points that would be on the inverse. Or in this case, it's easy enough just to say, well, I have a y-intercept of -4 and I got a slope of 3. And we'll connect those, do it in black. And so my black line represents the graph of the inverse. So I'm just going to go ahead and label these. This red was h of x, and the black is the inverse. And you can kind of see once again, they do reflect over, and it's always true for functions and their inverses, they always reflect over y equals x. Okay, any questions so far? All right, let's try this one. So once again, you can just pretend like this says y, and to come up with the inverse function, just switch places with x and y. So I'm going to make this read as x equals y minus 2 quantity squared plus 4. And now I'm going to go about the process, the normal routine of solving for y. So my first move would be to subtract 4. Now I need to undo raising this quantity to the second power, and I do that by doing the square root of both sides. And remember, when you do the square root of both sides of an equation, you have to include plus minus. And then I just have one more move to solve this for y, and I'm going to add 2 to both sides. It's not technically wrong if you do the order differently, but to avoid making this look like the plus 2 is going to be under the radical, I'm going to put it in front. And again, you wouldn't be wrong if you came in tomorrow and you said the square root of x minus 4 plus 2, but sometimes it's kind of hard to tell. And then now that I'm down to solve for y, and this does represent the inverse, I'm going to use the inverse notation. This is the inverse function. Okay, now let's sketch the graph of each. We'll start with the original function. This is a parabola, and the great thing is it's in vertex form. Remember that? And the vertex is what? What's the ordered pair of the vertex? 2, 4. Good. It has to open up from here. So let's just come up with a couple more points to complete the parabola. So let's just input 1 for x, just to generate an output. If I input 1, what's the output? 5. Good. And I have symmetry around x equals 2, so you get 1. It's like 2 for 1. Let's do one more. What about 0? Input 0, what's the output? 4 plus 4, okay. Everybody see how we got output 8? Okay, and those 5 dots will represent the graph of f of x. Now, I'm going to do the graph of the inverse, but instead of trying to do inputs, eventually you're going to know what this looks like in a couple of lessons, Well, let's just take the ordered pairs off of the original and switch them. And we'll have the graph of the inverse. For example, the point 2,4 is on f of x, so that means 4,2 must be on the inverse. The point 1,5 is on f of x, so that means 5,1 has to be on the inverse. And if you just take each one of the ordered pairs that we've already come up with and switch them and plot those, you're going to see how the inverse is really a parabola that opens to the right. And that should always be true. For the original parabola that opens up, its inverse should always open to the right. If the parabola opens down, the inverse should open to the left. And then you can check yourself. Do these two reflect over y equals x? And they do. Okay, so that should always be true. Original functions and their inverses should always reflect over that line. All right, so that's really a two-part answer. You need to come up with the inverse function, three-part answer, I guess, the graph of the original given function, and the graph of the inverse. Any questions so far? Okay, you got a few of these that are similar, but this little sentence right here makes it a little more involved, and we'll talk about that in just a second. So, first of all, let's find the inverse. So just for practice sake, again, treat this as y. Switch places with x and y. And then solve for y. My first move in solving for y, I'm going to multiply by 1/3. And then I'm going to do the square root of both sides. And it's okay, you don't have to rationalize denominators for this. It's okay if you leave radicals in the denominator. And this does represent the inverse, so again, I'm going to use that notation. So far, so good? All right, so now we've done the first sentence. And now let's graph the function. It's just a parabola with a vertex at the origin. Maybe I'll use blue. Okay, if you input 0, you get output 0. If you input 1, you get output 3. We have symmetry around the y-axis, so I can match up that point. Let's just do one more. I know it goes off the graph, but if I input 2, output 12. I think I'll just put that up here. All right, so this would be the graph of the f of x. And again, instead of trying to do inputs into the inverse and try to come up with that graph, it's a lot easier just to take these ordered pairs and switch them. Switch the xy coordinates. Well, they're both going to have the origin because obviously that's not going to change when you switch 0 and 0. The f of x has the point 1,3, so that means the inverse would have 3,1. And negative 1, 3 makes 3, negative 1. And this was 212 on the original, so we'll just say that this is 12, 2 way out here. And then the reflection over the x-axis. Okay, so we've graphed the function and its inverse. All right, now let's talk about this sentence here. If necessary, restrict the domain of the original function so that the inverse is a function. Right now, is the red a function? How do you know? I see Carly Okay, remember the vertical line test? If you draw a vertical line and touch more than one point, not a function. The blue is, but the red's not. The inverse of a parabola will never be a function itself. So what if instead of having this entire parabola, we only showed only part of it? So for example, if I only had this left side of the parabola and not the right, would the inverse then be a function? If you didn't have this at all, would it be a function then? Okay, and would that also be true if I just had the right half of this parabola and not the left? So, in other words, what this means is let's restrict the domain of this original blue so that that's what is actually going to take place. We're going to restrict the domain so that we only show half of this parabola so that its inverse will be a function. All right? So in other words, let's just say, for example, if all we had to look at, the only part of this parabola was just the left half, what would the domain be for just the left half of that blue parabola? How would you state the domain? And we'll use interval notation. Just the left half. Okay, I'm going to do that in blue. Okay, so just the left half of the parabola, we're going to treat it like two separate pieces so that we can represent the inverse as a function. And Carly's right, it would be from negative infinity to 0, including 0. Okay, so that would be the domain representing the left half. Okay, so if you look at this, we actually have two different, because of plus and minus, we have two different functions here. The positive represents actually one half of that parabola, and the negative represents the other half. All right, so think with me for just a second and see if you can visualize this. Remember that an original function picks up and flips over y equals x to create the inverse. So if you pick up this blue and flip it over, let me see if I can do it like this. If you compare the blue and the red, where is this half? Does it represent the top part of the red or the bottom part? If you pick this up and flip it over. The bottom? Can you see that? Because that's literally what happens. Remember that an original flips over y equals x, and you literally have to flip it over. Okay, so for the domain that represents the left part of this, we're going to let the left part of this domain restriction represent the negative of these two. All right, so here's my domain restriction, and that's going to go with this. The negative is the one that extends below the x-axis. I just need to get you to see, how do we know it's the negative one? Well, again, if you can visualize picking this up and flipping it over, this half corresponds to this half. Well, that just means then, what is the domain for the right half of the blue? What do you think? Katie, what's the domain just for the right half of this parabola?
Bracket 0 and positive.
Okay. All right. And that's going to correspond to the positive of these two. So domain restriction paired up with the negative. This domain restriction will be paired up with the positive. And did that make sense?
So is that the restriction? What did you say?
Yeah, we basically answered this last sentence, and it's really in two parts. These go together. This domain restriction matches up with, remember these are really two different equations. So this domain restriction matches up with the negative, and then this domain restriction will match the positive.
Oh, okay, so you just match like each side with the positive and negative.
Exactly. Yep.
Gotcha.
That make sense? We'll try another one. The directions are the same. I didn't write them all out, but I'm going to give you a little heads up when you get to problems 27 through 29. They're going to be quadratics in standard form. So this is good practice in taking standard form and converting to vertex form. And that involves some completing the square principles. If we can graph these in vertex form, it's so much easier. All right, so here we go. Let's change this first of all. Before we think about switching places with x and y, let's change this standard form to vertex form. So somebody tell me what number will go here in the parentheses.
3.
Good. Okay. Now somebody else tell me what number needs to be subtracted off of standard form to put this back into balance. -9. So what's going to be this number? -1. Everybody see that? That is vertex form. So that's nice because we can see the vertex. What is the vertex? 3, -1. And we can go ahead and complete the graph of this. Let's just do a couple more inputs. If we input 2, what's the output? 2, 0, which means I can match that point with this one. We have symmetry around x equals 3. And let's just do one more input. What about x is 1? What is that, Lakin, if x is 1? It should be positive, because this would be positive 4. 4 minus 1 is 3. Okay, so we already have the graph of the original. Now let's work on coming up with the inverse function. So once again, treat this as y, switch places with x and y, and solve for y. First move will be to add 1 to both sides. Then I'm going to do the square root of both sides, and don't forget plus minus. And now I'm going to add 3 to both sides. And since this does represent the inverse, I'm going to use the notation. There's the inverse of f. And once again, we need to come up with the graph of this, but I would just take these 5 ordered pairs, switch the xy coordinates within each, and plot those. So if you haven't done that already, go ahead. Starting with the vertex, that's 3, -1, so the inverse will have -1, 3. This is 1, 3, so I'm going to plot 3, 1 for the inverse. This is 2, 0, so I'm going to plot 0, 2. This is 4, 0, so 0, 4. And you can kind of see how, once again, a parabola that opens up should have an inverse that's a parabola opening to the right. Right, so far so good. And now all we have to do is, obviously the red is not a function, so let's do domain restrictions, break this original up into 2 pieces so that each piece would represent a function. So we'll just start with the left side of this blue parabola. What would the domain be for just the left half? Cooper, what would that be? Yeah, it's 3. It might be kind of hard to see. And that would be bracket. Okay, well, once again, you've picked the blue up, you've lifted it off the page, you flipped it over, and you sat it down in order to get the red. So just like in our previous example, the left half of the blue is really the bottom half of the red. So which of these two functions would represent this domain restriction? Would it be the positive, the plus, or the minus? The negative, yeah. So for this domain restriction, we're going to use this inverse. And then for the other domain restriction, which will be from 3 to infinity, we'll use the plus. What do you think? Make sense? Any questions? We good? Think you can do it on your own? If you think you're good, I'll skip this one. You think we're all right? Same instructions as the previous two. Okay. Real fast, you have 5 of these. And the directions are to determine whether each pair of functions are inverse functions. Are they inverses of each other? And here's how you'll know. And if you haven't seen this before, this stands for if and only if. Two functions are inverses of each other if and only if. If you do these composites, and in both cases you get x as a result, then they are inverses of each other. If you do these composites and you get something other than x, then they are not inverses of each other. So let me show you how this works. Here are my two functions. It doesn't really matter how you start. I'm going to do the composite f of g of x. That means take the g function, x minus 6 over 4, and put it in for x in the f function. And let's see what we get. 4 times x minus 6 over 4 plus 6. These 4's would cancel. We're left with x minus 6 plus 6, and that's x. So far, so good. But now I've got to do the composite going the other way. I've got to do the g of f of x. And if they truly are inverses of each other, then I'll get x as this result as well. So let's take the f function, 4x plus 6, and put it in for x in the g function. And it looks like this. 6 minus 6 is 0. 4x over 4. I got x there as well. So the directions say to write yes or no. My answer here would be yes. These two functions are inverses of each other. Okay, so real fast, let me show you a counter example. How do you know when they're not? Well, it really doesn't matter how you start. Let's just, again, we'll do f of g of x. Take the g function and put it in for x in the f function. Well, I've got to simplify under the radical before I do anything else, before I do the square root. And in simplifying under the radical, before I go any further, I notice I'm going to have minus 10. I'm going to have the square root of whatever minus 10. Well, that's not going to be x. Can you see how we're not going to get just regular old x out of this? So really there's no need to go any further. If I don't get x when I do both f of g and g of x, then they are not inverses of each other. And so my answer here is just no. I have to get just regular x when I do both composites. And last example, one way we can tell just by looking at a graph whether the inverse is going to be a function is by using the horizontal line test. We're pretty familiar with the vertical line test. What about the horizontal? Well, let's just do a rough sketch here. What's this going to look like? It's a parabola. Where's the vertex? 0, 0. All right, just one input. We'll do 1, 5. You don't have to get too fancy on these. So here's a parabola, vertex at the origin, and we got a total of 3 points. This is not going to pass the horizontal line test. And the horizontal line test is useful when we're looking at graphs to determine whether or not the inverse of this would be a function. And we've already established with previous examples that the inverse of a quadratic, unless we restrict the domain, the inverse of a quadratic function is not going to be a function. So my answer here would be no. Okay, do you remember what, this goes way back, and we'll come back and review this a little bit more as we get ready for the semester exam. Do you remember what the parent function f of x equals x cubed looked like? Yeah, it's kind of an S shape. Well, this is that S shape moved up 4 places, basically, is what this means. So I'm just going to do a rough sketch. Okay, the cubic function looks something like that. Will this pass the horizontal line test? Yes. So my answer here is the inverse of this would be a function. It would pass the horizontal line test. Okay, for these we're going to have to do some inputs and outputs. I know where it's going to cross the y-axis. It's going to cross at 12, and so to make this work, I'm just going to do these in 4s. Maybe we'll just do 4s for each. All right, I'm going to give you a little work. Let's input 2. Okay, so that'll be like half a mark. If I input 2 into this, in other words, do g of 2, what's the output? Or if you want to use synthetic division, you could do that as well. 12? That can't be 12. Is that on the same line? Okay. And negative 2 gives you the same thing? Try negative 2. Okay, well right away we've got 2 points that are on the same horizontal line. So is this going to pass? No. So on these little bit more elaborate functions, you're going to have to try out some inputs. You can always start with this constant as your y-intercept, and then just try some inputs that are pretty close to that. Start small and work your way out. Any questions? Think you got it?